Okay, let's get the rest of these examples done. So remember the next one we had to work through was the function given by, I'll just write the function down again so we have it on this page. G of t is equal to 2t to the fifth minus 4t squared plus 9. Okay, so let's calculate the derivative of this function. So we want to find g prime of t. So again, let's use the same strategy. We'll shift this to operator notation so it's a little easier to see exactly how we're applying the rules. So I'm just copying down the function. And notice I've written d dt instead of d dx, right? Because we're taking the derivative with respect to t, because t is the variable for this function. So that's why if you want to use operator notation, we should write it as d dt instead of d dx. If it was a function of x, we would write d dx like we normally have. Okay, so now let's take the similar approach for last time. Let's take a moment to break this derivative up because it's a derivative of one term minus another term plus another term. So let's break that up into three derivatives. So we can write the derivative with respect to t of 2t to the fifth minus the derivative with respect to t of 4t squared, and then lastly plus the derivative with respect to t of the constant term, 9. Okay, so let's apply the fact that each of these constant multiples can be pulled out, right? This 2 can come right out, this 4 can come right out, and actually this is just going to be 0, right? Because it's a derivative of a constant. So for that one, we'll just leave it as a plus 0 at the end. So here we'll have 2 times the derivative with respect to t of t to the fifth minus 4 times the derivative with respect to t of t squared. And then we've got this plus 0 here, which I'll just write down so it's clear what happened to this last term, right? It's just 0 because 9 is a constant. Okay, and then now we're going to apply the power rule again. So remember the power rule? If you have a function of x given by a power of x, you can always write the derivative of x raised to the power of n. If n is a constant, it's just given by the formula nx to the n minus 1. And now there's nothing special about the letter x. That means this only works for functions of x, right? We have a function of t. Really all that matters is that this variable matches up with the base of your power and that your exponent is constant. Okay, so that happens here, right? This variable down here, the derivative with respect to t, and our power is a power of t. That means we can apply the power rule here. So we're going to get 2, because that 2 is outside. So if you apply the power rule here, you bring the 5 down in front. So it's like 5t to the 5 minus 1, which will be 5t to the 4 in this case, right? So you subtract 1 from the exponent, and that's what you'll have as your new exponent. Okay, then over here we'll have minus 4 because that multiplier is out front. And then if I take the derivative of t squared, I'm going to have 2t to the 1. Or you can just write 2t if you like as well, that's fine. But then now the derivatives are done and we can clean this up. So let's multiply the 2 back in and multiply the 4 back in, and we'll have 10t to the 4 minus 8t. I'm not going to write 8t to the 1. That would be not helpful. So I might as well just write it as t, right? The exponent 1, I wrote it here just to make it clear how the power rule was applied. But once you have an exponent of 1, you don't really need to write it. It's automatically there. Okay, so that's good. That means we're done. So now we can say, okay, therefore, let's just squeeze a summary in over here. So therefore, g prime of t is equal to 10t to the 4 minus 8t. That's how we can summarize our answer. Okay, great. So that takes care of that example. And you can see the idea is we break them up term by term, break these functions up term by term, and then pull out all the constant multipliers to the point where now we have just derivatives of powers, and then we apply the power rule to each derivative. And that's really your strategy for taking the derivative of polynomials at this stage. Okay, let's do the next example. So if you remember for part C, the function was y equals x cubed plus 4 cubed. So I'll just write that down so we have it in front of us. Okay, and let's go ahead. So you can write dy dx, or you can write y prime. Both of those would be valid notations for the derivative of y. I'm going to write y prime this time, just because I like that notation the best. It's just the briefest. So y prime is the derivative with respect to x of x cubed plus 4 cubed, right? I'm just shifting into operator notation again. I haven't done any work yet. Okay, and now I'm going to break this up into the derivative with respect to x of x cubed plus the derivative with respect to x of 4 cubed, and then I'll differentiate each of those terms separately. So the first one, this is nothing new, it's another power rule, right? In fact, it's the same power we computed in the original example. We can just you bring the power down, bring the 3 down in front and subtract 1 from it. So the derivative with respect to x of x cubed, that's going to become 3x squared. It's just a direct application of the power rule. And now for this one, we've got the derivative with respect to x of 4 cubed. I always write it this way just to maybe give people an opportunity to make a mistake, just so that I can also, and then we can take that opportunity to correct that mistake. If you're trying to get ahead of me and you wrote 3 times 4 squared, if you apply the power rule here, what you're probably doing is you're forgetting that this 4 is a constant. The power rule applies to terms like this because that base, x, matches up with the variable you're differentiating with respect to. But here, 4 cubed is a constant. It doesn't matter if it's 4 cubed or if it's 4 to the power of 20 or if it's how big or small of a number it is. If it's constant, its derivative is 0. So we're just going to get plus 0 in this case. So your derivative is just 3x squared. So you can say, therefore, y prime is equal to 3x squared. All right, so don't fall for the trick of if you have a power of a constant that you fall for the trap of applying the power rule to it. Because if it's a constant, if the base is a constant, then the whole term is a constant. And that means you're going to just apply the fact that the derivative of constants is always 0. Okay, part D. What was the function for part D? We had y equals pi times x. Okay, I want to make a note before we finish this one. There's a convenient observation you can make, and it really helps to make this observation and also to remember it. It can save you a lot of head scratching. So first, let's say we had the derivative with respect to x of just the function x. So the identity function y equals x, or f of x is equal to x. But let's just say we were dealing with that directly. We want a derivative with respect to x of just the identity function x. Well, if I write that as a power, just to make it really, just to really exaggerate the fact that I can use the power rule here. X is actually x to the 1. And once I write it as x to the 1, then that would fall under the power rule. And I could use the power rule and take its derivative to be 1 times x to the 0. Right? Really what I'm doing is I'm just applying this rule to x to the 1. So the result is going to be 1 times x to the 1 minus 1. That's how I get 1x to the 0. But x to the power of 0 is just 1. So really, you just have 1. So as a consequence, you can say that the derivative with respect to x of the identity function x is just 1. It happens so frequently that it's worth remembering. More generally, let me do a more general case, and then we'll actually circle it in red again so we can add it to our list of rules. So more generally, if I had, let's say for a constant c in the reals, so a real number c that's constant, so let's say for c in the reals, where c is constant, I better be careful to say exactly what I mean here, we have the following. I can say the derivative with respect to x of that constant times x. Well, if I was trying to evaluate something like this, I might say, okay, well, constant multiples can be pulled out of derivatives. So I'd get c times the derivative with respect to x of just x. But we just worked this out, right? This is equal to 1. We just set that up here. If this is equal to 1, then we're going to have c times 1, which is really just c. So that's the summary I want you to take away from this little side discussion. So therefore, for any constant real number c, the derivative with respect to x of a constant, of that same constant times x, is just going to always work out to be c. That's the part I'm going to put a box around because I want you to be aware of that. And it's really useful to know those, to know how to do these calculations by heart. You really, what it comes down to doing is you're applying the power rule to powers of x that don't always look like powers of x. Like just x on its own, technically that's a power of x if you write it as a power of x. Okay, so that's, I'm just going to separate that off because that's a side discussion. But it's really useful to just know these calculations by heart and keep them fresh in your mind. And basically it lets you do derivatives like this very quickly. So really, because we can say that, that y prime now is the derivative with respect to x of pi x, which by this rule, just take c equal to pi, and the result is just going to be pi. So we get pi. Okay, so that's our, just if I'm following the same convention, I can say therefore y prime is equal to pi for this example. All right, we have one more example, f of x. Let me just copy the function down again. We have f of x was equal to pi x cubed plus the square root of 2 times x. So that was the part E of this example. So let's find f prime of x. So let's look at this in the following way. I could change this over into operator notation, but let's just ask ourselves what we're going to do. Right? We've got two terms, so we're going to differentiate them separately. We know that. That's how we've been tackling all of these examples so far. So we don't need to switch to operator notation to do that. There's nothing stopping us from just saying, okay, well, let's work out the derivative of pi x cubed. We'll write down that derivative, and then we'll say, okay, now what's the derivative of the square root of 2 of x? Or pardon me, the square root of 2 times x. And then whatever the derivative of this term is, we'll just add it on after, and then that will be our answer. If we can do that, let's just do that. Okay, so but then how do we handle the pi x cubed? Well, pi x cubed is not quite a power of x, so we can't quite perform the power rule on that directly. But we know what we're going to do, right? Let's go back up here. What do we do when we had multipliers? Like what about a term like this, 2t to the 5th? Right? We wanted to apply the power rule to t to the 5, but what happened to the 2? We pulled it out in front, right? And then we did power rule on this, and then we took the 2 and multiplied it back on after. So why don't we just do that without writing out all the operator notation? And that's typically what most people will do. So we'll look at it this way. Okay, pi is a constant. Let's just put it off to the side, and we'll remember, we won't forget that it's there. We're just going to tuck it off to the side, and then now we'll focus on the x cubed. What's the derivative of x cubed? We'll apply the power rule to that, and you're going to get 3x squared. Okay, and that's all there is to it. Now the pi will get multiplied on after, but that's what we've already written down, so we don't even have to worry about it now. Just write down your constant multiplier, then take the derivative of the power, put it in brackets, and then you're done. We're done with that term. Now what about this term? Well, we can differentiate the square root of 2 times x. Well, what this kind of looks a lot like part D, right? We had a real number times x, and we wanted to differentiate it. And it turns out that this constant multiplier just ended up being the answer, and that follows from this rule. If you have a constant times x, and you take the derivative with respect to x, you just get whatever the constant is. So in this case, this is going to fall into this rule again, but with c equal to the square root of 2. So you're just going to have plus the square root of 2. So that's not too bad. Okay, and that's an example. Notice that both of the terms had irrational numbers as multipliers here. Like the constant multipliers were pi and the square root of 2, but so what? Nothing changed, right? We didn't have to do anything different, just treat them like real numbers. It doesn't change the fact that this is a polynomial because they're just whole positive integer powers of x cubed and x to the 1. The coefficients just happen to be irrational numbers, but who cares? Okay, so, but we could still clean this up a bit because usually you wouldn't write your answer like pi times 3x squared. That looks like there's still work to do. Even though we're not going to change much, it's better to write this as 3 pi x squared plus the square root of 2, and we can say, okay, therefore f prime of x is 3 pi x squared plus the square root of 2. Okay, now someone's bound to ask me the question, do I have to do this? Do I have to summarize and say, therefore the derivative is this? I did that in every single example. I summarized the derivative at the end. You don't absolutely have to, as long as your work is clear and easy to follow, but it's always a good practice to do, and to take a moment to actually separate your answer and put a box around it to highlight it and kind of show a summary of your work that's easy to just glimpse at. And also, it can kind of buys you a little bit of freedom if your work is a little bit not quite so organized, then all the more a reason you should do this, because then it's just going to draw attention to the answer, because that's what you want to do. You want to draw attention to the answer. Okay, so that's the end of that example.